AC through pure inductive circuits. A pure inductor means an inductor without any ohmic losses. In this circuit you can see that an alternating voltage source is connected across an inductor, and when the switch is closed, an alternating current will be set up in this circuit. And because of the flow of the alternating current, that is a time varying current, a self-induced EMF will be induced across the terminals of the inductor. The direction or the polarity of the induced voltage is according to Lenz's law. According to Lenz's law, the direction of the induced voltage will be in such a way that it will be opposing the very cause of its generation. Here you can see that the cause of generation of the alternating current or the self-induced voltage across the inductor is the time variation of the current passing through that, which is caused by the time variation or the alternating property of the voltage source connected across it. Now, if you assume the polarity of the induced voltage at this point at some instant is positive, at the same instant, according to the Lenz's law, the polarity of the induced voltage at this terminal will be positive. Now, if you apply Kirchhoff's voltage law to this law, you get an equation Vt minus Vlt is equal to 0, because there is no other element where there is a voltage drop. And you know that the voltage across the inductor is given by L into di by dt, where L is the self-inductance of the coil and di by dt is the rate of change of current through the inductor. So, if you from the Kirchhoff's voltage law equation, we get V is equal to L into di by dt, where V is the applied voltage, which can be represented as Vm sin omega t is equal to L into di by dt. From here, if you rearrange, you get di is equal to Vm by L into sin omega t. Because here we are representing the sinusoid or the alternating voltage in its standard form, Vm sin omega t, and we are considering that voltage as reference when we do the phasor analysis. And from here, if you integrate on both sides, you get I is equal to Vm by L into integral of sin omega t dt. That is, I is equal to Vm by omega L. When you integrate sin omega t, you get minus cos omega t by omega, and this L is there. So finally, you get I is equal to Vm by omega L into minus cos omega t. Now, minus cos omega t can be written in terms of sin omega t with some phase difference. That means sin minus cos omega t can be written as sin omega t minus pi by 2. This is obtained from the relation cos omega t is equal to sin pi by 2 minus omega t, and sin of minus theta is equal to minus sin theta. If you combine these two properties, you can write minus cos omega t is equal to sin omega t minus pi by 2. From here you can see that if you consider the voltage signal as a reference, you can see that the current signal or the current waveform lags with respect to the voltage waveform by an angle of pi by 2 radians. And from here you can see that if you consider this as the maximum value of the current waveform can be written as I is equal to Im sin omega t minus pi by 2, where Im is given by Vm by omega L. And here you can see that the current waveform or the current waveform is lagging with respect to the voltage waveform by an angle pi by 2 radians. For that only we have converted I converted the waveform or the equation for the current into sine form. Then only we can compare these two signals. Here you can see that this is the applied voltage and this is the applied current. Now, if you plot the voltage and current waveforms, voltage waveform is given by Vm sin omega t and current waveform is given by I is equal to Im sin omega t minus pi by 2. Here Vm is the maximum value of the voltage waveform, and here Im is the maximum value of the current waveform. See, if you plot this V and I, here you can see that this is the plot of the voltage waveform and this red one is the plot of the current waveform. Here you can see that this is the phase difference between the voltage and current waveform, and here you can see that the current waveform is lagging with respect to voltage waveform by an angle of pi by 2 degrees, which is evident from this equation. I is equal to Im sin omega t minus pi by 2. Here, now you can see that from these plots, this is the applied voltage V, and this green waveform is the plot of the self-induced voltage across the inductor. Here you can see that at any instant the polarities or the direction of the voltages are opposing each other. And here we can see that the current through the inductor is lagging with respect to the voltage. That means if we are considering this waveform as reference, so this waveform is lagging with respect to the reference voltage by an angle of pi by 2 radians or 90 degrees. Now if you draw a phasor diagram to convey this message or to represent the information obtained from this voltage waveforms, here you can see that here we are taking the voltage phasor as a reference. So the applied voltage will be taken as or it will be drawn along the positive direction or x-axis or in the reference direction. Here you can see that this is the voltage waveform where VL is the RMS value of the applied voltage and IL is the, and here actually it is the VL means the voltage applied across the inductor, and IL is the current flowing through the inductor. Both are representing the RMS values. So here you can see that if you consider this as a reference, IL is lagging with respect to the voltage by an angle 90 degree. And here, and sometimes we may have to take the direction of current or the direction of the current phasor as a reference. In that case, from this phasor diagram, you can see that if you consider this direction as a reference, the voltage phasor will be leading with respect to the direction of the current phasor by an angle 90 degree. That information is conveyed by this phasor diagram. Here you can see that we are considering the direction of the current through the inductor as reference. In that case, the voltage across the inductor will be leading with respect to the current through the inductor by an angle 90 degree. So the waveform corresponding to this is drawn here. Here you can see that this waveform is taken as a reference. So if you consider this waveform as reference, the voltage across the inductor will be leading with respect to the current waveform by an angle pi by 2 radians. That is obtained from this waveform. And here you can see that both phasor diagrams are conveying the same information. So we have seen that the current through a pure inductor lags the voltage across it by 90 degrees or pi by 2 radians. From the discussion, we have seen that Vm can be written as Vm is equal to omega L into Im. That's actually obtained from the equations what we have seen earlier. So Vm can be written as Im into XL. And here you can see that you can compare this with a purely resistive circuit. There the current is given by I into R in case of a purely resistive circuit. So instead of R here, in case of a purely inductive circuit, we have a term XL which is given by XL equal to omega L, which is given by 2 pi f into L, where f is the frequency of the applied alternating voltage, and this term XL is known as the inductive reactance, which is represented in ohm. And from these relations you can see that the maximum value of current I given by Im is obtained by Vm by XL, or the equation Im is equal to Vm by XL, where Vm is the maximum value of the voltage and XL is the inductive reactance of the coil. And the RMS value of the current through the inductor is given by Im by root 2 is equal to Vm by root 2 by XL. That is, RMS value of the current is obtained by RMS value of the voltage divided by the inductive reactance. From these relations, you get I, the capital I, which is the RMS value, that is equal to V by XL. So you have to remember these two relations. And from the phasor diagram, you can see that V is represented as V angle 0, because here we have taken voltage as reference. So V angle 0 divided by I angle minus 90 degree, because here I and voltage and current are represented in polar form. So if you consider the direction of the voltage as reference, voltage waveform is represented as V angle 0, where V is the RMS value of the voltage and current will be represented as I angle minus 90 degree, because this minus 90 degree is the phase difference between the reference voltage and the current. So from here V by I you get XL, and from here you can see that XL will be having a angle of plus 90 degree, which is represented as J here. So in Cartesian form or in R plus J XL form, the pure inductor is represented as JXL, and in the polar form it will be represented as magnitude XL angle 90 degree. And if we consider the variation of the power in a purely inductive circuits, the instantaneous power in a purely inductive circuit is obtained by the product of the instantaneous values of the voltage and the current. That means P at t, Pt means power at any instant is equal to Vt into It, because both the voltage and current waveforms are time varying. So Vt is represented as Vm sin omega t, and It is given by Im sin omega t minus 90 degrees. From here you can get Vm sin omega t minus 90 degrees. Sin omega t minus 90 degrees is changed to minus cos omega t. From here you get minus O Vm Im by 2 sin 2 omega t. Here you can see that the frequency of the power waveform is double that of the frequency of the voltage waveform. Here you can see that the angular velocity is omega here for the voltage waveform, and here you can see that the angular velocity of the power waveform is 2 omega. That means frequency is double. That means the variation of the or the time period of the voltage time period of the power waveform will be half of that of the voltage waveform, or the frequency of the variation of the power. This is the power variation. So you can see that the frequency double that of the frequency of the voltage waveform, because here you can see that a cycle of the voltage waveform starts from here and is up to here. This is the time period of the voltage waveform, but for the power waveform you can see that it has completed 2 complete cycles. That means frequency is double that of the voltage and current waveforms, and the period is half that of the voltage and current waveforms. Here you can see that if you consider the average power over a complete cycle, here you can see that the positive part and the negative parts are exactly matching. That means if you add it up for a complete cycle, you will get 0. That means it can be obtained from mathematically by this formula. P is equal to 1 by 2 pi integral from 0 to 2 pi pt d omega t. Actually we are integrating the power waveform over a complete cycle and taking the average, and you will be getting it as 0 because it's a perfect sinusoid. And here you can see that at this instant power will be drawn by the circuit, and during the next half cycle of the power variation, the power will be sent back to the circuit. So in effect, over a complete cycle, the average power consumed by the circuit is 0, or that is actually the definition of the pure inductive circuit. In a pure inductive circuit, there is no ohmic losses. That means no power is consumed in the circuit. The average power over a complete cycle will be equal to 0.